Hi, this is Christopher Boucher, and I'm going to review an introduction to sampling distributions. Okay, we'll get started. So we have sampling distributions, and also included with sampling distributions are proportion types of sampling distributions. Technically, you can have a sample that's proportion based, but those are included as well. So sampling distributions conceptually are, I would say, difficult, although the actual application is not that much different than finding probability with, say, a normal distribution. But to get to that point, we kind of have to have an understanding of what we're doing, and that's what I'm going to talk about here. Okay, so sampling distribution is a distribution of all possible statistics, meaning a means of samples. So technically, we have this distribution curve, and it's made up of a lot of, or all of the possible, in theory, all of the possible different types of samples, and all of the means. And there's later in these notes, there's a graphic picture of that. But the idea is, as we keep doing samples and we have all the samples of a distribution, we actually, now in theory, let's say you have a population, but populations are hard to work with. So what we do is we can do a sample, and theoretically, if we do a lot of samples of large samples, then we take the means that we get from those samples, and we can actually determine if it follows a normal distribution with a couple rules, and the empirical rule and different things like that, central limit theorem. Then we can go and we can kind of make it a bridge where we go from the theory of populations and normal distributions all the way over to the sampling distributions, and it allows us to apply more of a conceptual way of doing kind of inductive reasoning with statistics. Okay, so let's take a look at this. It says samples must be all of the same size. So in theory, if we had all of these samples of the same size are taken from a distribution, and we get the means from all of these samples. So it says, well, complete all possible samples perform sampling distribution is more conceptual than practical. We can work with the concept and apply it by creating our own limited sampling distributions. Sampling error and central limit theorem, discussed later, is closely related to the concept of sampling distributions. Okay, so the idea is, as the samples get smaller, the sample size gets smaller, then what happens is we end up introducing more error, and that has to be accounted for, and I'll show you how to account for that. Okay. So these are characteristics of a sampling distribution. It says sampling distribution, and then it says number of samples. So samples are limited to practical ability. So in theory, like I said, this is very conceptual. Sampling error. Sampling error is related to the sample mean difference from the population. And then it says mean value. The sum of all sample means divided by the number of means. So if you can imagine getting an average of averages, we'll become closer to the population mean as the number of sample means increases. So if we get all of the possible configurations of samples and we get the means from those, then we should be really close to the population. And that's essentially what they're saying. Then it says steps to create a sampling distribution. It says take several samples with replacement of equal size from a population or process. For each for each sample, calculate the mean, create a frequency distribution of the sample means. Okay, so I'll show you kind of how this works. So we have, we have a very small, I say small because these work better as we get really large populations and big samples. But in this one, I think we have 60 observations. 1, 2, 3, 4, 5, 6. Oh, maybe not. and then 1, 2, 3, 4, 5, 36. So we have 36 total, and that's down here. Okay, so we have 36 observations, and then we're going to create a sampling distribution, and very limited, with a lot of different samples. Of course, there's more possibilities that we could do, but I wanted to come to a way of making this so that you can actually see where the samples are coming from. So in this case, we have this population data, because this is all of its 36 numbers, and then we get the population mean. So we add up all the numbers, divide it by 36, and our population mean is 5.111. Okay, so that's our population mean. That's the gold standard for what we're working with. So then we go and we do a bunch of samples. So we're trying to now take a bunch of samples from this population. So in theory, we don't have access to all of the population data, but we can do repeated samples, and we can do a lot of these, and if they're good randomized samples, it's going to tell us something, and we can work with that. And so there's a couple different ways you can look at this thing. So these right here that are like a light, like peach color, that's one group of that's one sample set. The light blue, that's one sample set. The darker orange, that's a sample set. The light green, then the peach, light green, these are all sample sets. And then let's see, as we go, I believe, then as we go vertical, these are all sample sets, and then there's some, maybe there's some DAG. No, that one's already accounted for. So I went and I did verticals and then horizontals, and then I go and I got the means of all of those. So I added up the numbers, divided them by 6. They all have the same, they have to have the same sample size. So we did that, and then I put them on a frequency distribution chart. So it's a frequency distribution of sample means. And so, so I put those all on here. And I also calculated the sampling distribution mean, or the mean of means, if you want to think about it that way. And what's actually interesting is I did not anticipate it'd be this close, but it is super close, 5.110, and that's the sampling distribution mean. So that's kind of a weird, amazing, fortunate thing. So it was actually really close. And then we go and I actually drew out the distribution. So and it makes sense because there's a higher frequency in the middle, although it's obvious that it's not super concentrated. And then it says, so the sampling distribution mean is nearly identical to the population mean. So here's the population mean, and here's the sample distribution mean. And it says, while the calculated sampling distribution graphic above does not contain a large number of sample means, one can see the frequencies of means are beginning to cluster around the middle. So if we only did 18 samples, if we went and did a lot more samples, I would expect we'd see clustering, and we'd actually see the same distribution shape as the population. The other assumption is the population is normally distributed and everything like that. But this was just to show you what a sampling distribution kind of is. And like I said, it's sort of very conceptual, but it provides the bridge. And the reason why we do the sampling distributions is because it's a way that we can calculate error from doing a sample from a population, and along with that we can like I said, we can calculate the error, and then we can go and we can start doing confidence intervals. We can do hypothesis testing, because we usually can't work with population data, and that's the whole deal here is that we have non-perfect data, and the sampling distribution allows us to work with that, and it's because some of the assumptions are based on it being normal and things such as that. Okay. So now we're getting into the theorems here, and these are the central limit theorems. As I mentioned up at the beginning of this, there's a couple key parts to it. It says The central limit theorem is a important concept of this with the sampling error. Okay, so like I said, just listen to me as I go through this, and then I'll show you the math is not very difficult compared to the theory. So you can still do this work even if the theory is a little bit out there. So bear with me. So theorem 1. For any population, the average value of all possible sample means computed from all possible random samples of a given size from the population equals the population mean. Okay, so we take all of the samples from a population of a certain large size, and we get all of essentially the permutations, combinations, and it should equal the population mean. Well, yes, because by the time that we are getting all of the samples in such a large number, we're essentially duplicating the population mean. And it says when the sample statistic equals the parameter, so back at the beginning of this class, I spoke about a parameter is actually a characteristic of a population, whereas statistic is a characteristic of a sample. And so when they say the sample statistic equals the parameter, what they mean is the sample mean equals the population mean, essentially. So irrespective of the value of the parameter, the statistic is called an unbiased estimator of the parameter. What that means is it is because the sample is so close or actually the same as the population parameter, then it's unbiased, because what that means is it doesn't have any bias, which is another way of saying error. So what that says is this theorem 1 is you take all the possible samples that are possible, and very large samples. In theory, you want the samples to be the actual size of the population, just random, almost the size or the size of, once again, we're kind of in the theory zone. And you do that enough, and you're going to come up with some number that is super close to the population mean for your sample mean. And then we're going to call it an almost unbiased estimator. Okay, so that's the first concept, and that is you keep doing enough samples that are big, and it's going to come really close to the population mean. So theorem 2, for any population, the standard deviation of the possible sample means computed from all possible random samples of size n is equal to the population standard deviation divided by the square root of the sample size. The formula listed below is also known as the standard error of x, alternatively, the standard deviation of the sampling distribution. I sometimes use both terms. I think sometimes I call it probably more the standard deviation of the sampling distribution, because I think that's what it looks like. So it says an important implication of this formula is that the sample size must be quadrupled, multiplied by 4, to achieve half the measurement error. So to reduce the amount of error from this calculation, we have to quadruple our sample size. So it's because the effect of getting the root of n right here. So the big take-home thing is we want big samples. That's the big take-home message. And as we have small samples, then we have a really large error, and that's the take-home message here. It says when designing statistical studies where cost is a factor, this may have a role in understanding cost-benefit trade-offs. So sometimes what people do is they want to figure out a study, they want to make a study, they want it to be within a certain precision, accuracy. This could be a confidence interval. Take, for instance, you hear of surveys where they say plus or minus a certain degree margin of error. So if you want to make it so that it's within, say, 1 point standard of error or whatever, 1 degree, whatever value we're working with, you have to have a really large sample, and so that's why sometimes you'll see these samples that aren't that big, or surveys that don't have a really big sample size, and they'll say plus or minus 3, and it's because it's kind of tolerable, but it's not that close if you think about plus or minus 3. It gets really expensive is what this last line is talking about. To reduce that by half of the measurement area, you have to quadruple your sample size, which is expensive if you're calling people up or something like that. It says, without the standard deviation of the sampling distribution formula, it would be difficult to impossible to perform specific calculations that require a sample standard deviation. Bingo. So, if we need a sample standard deviation, we wouldn't be able to do it. We wouldn't be able to discern what the sample standard deviation would approximately be if we didn't have this formula right here. We would be stuck, and we wouldn't be able to do some of our testing. So number 3, if a population, okay, so this is the part that is, I guess, slightly different. In a slightly different way, it's stating what we just talked about. And that is, it says, if population is normally distributed with a mean, mu, population mean, and standard deviation. So we have a population mean and a population standard deviation, the sigma. The sampling distribution of the sample mean is also normally distributed with a mean equal to the population mean and a standard deviation equal to the population standard deviation divided by the square root of the sample size. So what it means is if our population is normally distributed, then we can calculate out our standard error of x, or our standard deviation of the sampling distribution, and we can work with that, and we can work with that essentially as in a similar way of kind of like our sampling standard deviation, sample standard deviation. So it allows us to kind of fill in some of the parts, and that's the big thing here. And then theorem 4 is the central limit theorem, establishes the concept that as independent random variables are added, their properly normalized sum tends towards a normal distribution, even if the original variables are not normally distributed. So this is really important. So the idea is we take a lot of, let's say in this case, sample means, and we put them all together. If we just have 3 of them, we could say, wow, those numbers are way off. They're way different. But as we increase the sheer volume of the sample means and we put them all together, what this is saying is as the size increases, it'll actually normalize, and we will have more of a normalizing effect. And that effect typically, this isn't set in stone, but statistically and scientifically, most people agree this happens around 30, although that's debatable, like lots of other things in statistics is debatable. But 30 is something that is considered a standard number for that. And this diagram shows that. And what it is this says it is sufficiently large. So we have a sample that's, let's say 30. We say, oh, well, the data must be normalized because, the sample is big enough. And big enough in this case is 30. Now, you can see here that so 30 is right. It's actually, the little point thing is a little bit low on this. Sometimes you edit these files and the things slide down, but it's right here. I'm just looking at, oh, no, that's right. It's just the way they set this up. So 30 is this one. It's the little pointer's in the correct spot. So 30, you see it's pretty smooth. But if we go back, 29 is not bad, 28 is not bad, 27 is not bad. These are computer generated random numbers, I believe. I think I probably got this from Wikipedia. They have some good stuff with statistics here and there, at least graphic wise. And so as we back up, it's interesting the way they did this. The number is actually on the top. Um, so as you back up, you see that it becomes a little bit more random, and it'll flatten out or it'll get really lumpy. This one right here is 20. But as we go to like 5, it's very inconsistent, and you never know what you're going to get, type of thing, like a box of chocolates, right? So so like this is 18 right there. So 30 is typically considered okay, but some people would be fine with 28 or 29, and it kind of matters what you're working with and some of the tolerances in your testing. So a couple things here while we're talking about this. If we take samples from a normalized distribution, typically they consider that to be normalized. Um, there's a little bit of wiggle room in the way that we apply the normal distribution. In most of the questions in my class, I try to make that clear, only because I think sometimes people know how to solve the problems, but if the problem isn't clear which distribution we apply or which type of test we apply, they miss the whole thing, and they could have gotten it right if the question was more clear. So I try to make it clear. Usually I will either have certain parts missing, or they'll be there or they'll be missing, and then usually the distributions will be above 30 or higher or not, or I will make it crystal clear that this follows a normal distribution. So I try not to trick people. Okay, so we've been talking about samples. So we have samples, which are sample means is usually what they're based on, sample means, and then we have proportions. So a proportion, if we think about it, a proportion is just another way of kind of doing a type of testing. And with a proportion, we usually have a population proportion, and that's just saying, hey, there's a certain, if we think about proportions, we can think about pie charts. So we have a certain slice of a certain group of a population that has a certain characteristic, and that's a proportion. And they're typically written as a fraction or a decimal, essentially 0 to 1, and the proportion value is somewhere in the middle of that. So what we can do is we can use that as our population. So we have this proportion value, and it is, they say, oh, well, this characteristic proportion is typically 0.6, 60, or essentially 60% of the population. And we go, okay, well, and that's a population proportion. And then what we can do with this is, depending upon how this is all laid out, we can go and we can apply the standard normal z distribution, normal distribution to it, but actually use the z distribution to solve our questions. And the other thing is, there's a lot of people who teach the proportion part first, and I started doing that. I had went to a conference once, and the person that was there really pushed the idea of doing this, and I started teaching the proportion part first in this unit. And I think it works pretty well because we don't need a population standard deviation when we're doing proportion types of questions like this. And that, in a weird way, is a little bit easier. At first, it seems awkward if you're used to doing sampling calculations, but then you look at this and you're like, oh, that's not too bad. So it says, whereas the prior diagrams utilize sampling mean and a population mean mu proportions, we can also perform sampling distribution probability calculation with proportion. Okay, while the previous pages explain the theory of sampling distributions with sample mean, all the concepts apply to proportions. Many believe the sampling okay, to be easier, because that's just what I said. Okay, so let's look at these. This top part is proportions. This second part down here is sampling distributions. So here we go. And I kind of break it down early on because some of these symbols are new to us. Okay, so when we talk about sample proportion that we're testing in is, okay, so the sample proportion we're testing for and is equivalent to, it's like our x bar right there, and that's when we have the p hat right there. And then the big P is the population proportion. So that's the end all be all for this. This is our population value there. Parameter would be the right term. And then we have the z-score formula. So this is just like our other calculations where we got the z-score and then we look it up on the table, except this one we're just using proportion values. And you see we have p hat, subtract the big P, and it kind of makes sense because on the other one this would be x bar, subtract x bar, let's see, x bar, subtract, it would be mu, I believe, and then down below it would be the standard deviation, I think. So off the top of my head. So with proportions, we can just do the same thing, and we can apply this. And this bottom part right here, this is the sampling distribution part that's new to this chapter. And this is it right here. This sigma with the p hat right there, this is the same thing. So once you solve this, you can just plug it in there. And so I actually solve this one first. I take that value, and then I do this one, and I just plug that right in there because this whole thing is that whole thing right there. So this is actually the sampling, the standard deviation of the sampling distribution of the p hat. And then down below here, let's see, the p hat e, that's just the sampling error of p, or yeah. So and if you look at this, so we have the proportion sample, and then the population parameter proportion right there, and that's all that we're just finding the difference. Okay. And then this is the sampling distribution formulas. So these will probably look a little bit more common to you, but the new part is the denominator section, and that is this part right here. So since we don't have the on these, we don't have the sample standard deviation, what we do is we get the standard deviation of the sampling distribution, also known as the standard error of x. And you see, all that this is we use the population standard deviation, but with the caveat that it's based on a certain sample size. And as that sample size increases, the amount of error or the difference decreases from the actual population standard deviation. And that makes sense because as our sample gets larger, we're actually getting closer to the actual population data. And then right here, this is the same type of z-score formula that we've used, except this part right here is just different. And that is because, let me see if I can zoom in just a little bit more. And that is because, like I said, this is a sample, and so we have to account for it. So this is the z-score formula for the sampling distribution of x. That's the only real big difference here. And then this is the error. So the x bar with the e. So the error is always just, this isn't the standard error, this is the sampling error. Standard error is a little bit different. But this is just the sample mean, subtract the population mean. And it makes sense because the error means that's its level of inaccuracy. And it can be plus or minus, right? That's why they usually say plus or minus, because they don't actually know what it is. That's because they're samples. They won't know until after the fact, say with certain surveys. Say like polling surveys of what people are going to vote for, they don't know until after the fact. Then they can calculate how far off they are. Okay, so let's take a look at how we apply some of this stuff. So this is proportion sampling error. It says a population is made up of 70% proportion of a specific attribute. So 0.70. If a sample is selected and the probability of success in the sample is 0.65, what is the sampling error? So what we do is we say, okay, well, in the population it's 0.70. In the sample it is 0.65. So we're actually, the sample is actually biased. It's actually wrong, negative 0.05. That should make sense. And then for the mean sampling error, we say, okay, a population consists of a mean of 130 and a standard deviation of 400. In this case, we don't actually need the standard deviation. I just threw it in there. If a random sample shows a mean of 140, what is the sampling error? Okay, so we see our sample shows the mean of 140, but the population is actually has a population mean of 130, so we know that our sample is a little bit high, and the actual sample mean is a little bit high, so it's a sampling error of, let's say, of 10. If we're looking at the other ways, it would be like plus 10, so it's positive 10. Okay, now let's look at how we solve this. Now, in the last unit, what we did was we started the concept of using population data and finding essentially what I call the area under the curve, or the probability of obtaining a certain point estimate. So it was essentially a point estimate of something was going to be at a certain point was going to be less than or more than is typically the way it's set up. So in this one, these are proportion ones first. So it says, based on the 2010 census, the proportion of adults who own their home is 40%. If a sample of 1,000 adults is conducted, what is the probability of the ratio being less than 42%? So we say, okay. And these numbers, I really don't know what the real numbers are. I think I made them up. So we have our population value right there, which is 0.4. And then the proportion, it says what is the what is the probability of the ratio being less than 42%. So P is less than because it's facing towards the 42, less than or greater than. So 0.42. So we always lay out what we lay out what we know first, and that is so that we don't get confused later as we're trying to apply it. So make sure your inequality is pointing in the right direction right from the get-go. Otherwise, you will not be able to get the right answer. And then what we do is I always do this one first. I always essentially I'm calculating the standard deviation that we are going to be using for sampling distributions, whether it's proportion or sampling distribution. So I always do that first, because once I get this value, I can just plug it right in the bottom part here and get the z. So, and you have to get that before you can actually get the z-score anyway. So we just plug these things in, really easy. Like I said before, we have a limited number of numbers to work with here because we don't have a standard deviation. We're just working with a proportion. So if you look at this, we have 0.40 goes right here, and then this is still 0.40. They're actually finding the inverse of that, right? Because they're subtracting it from 1. And then the n, which is 1,000. So it's real easy. If you're not super comfortable with the calculator, solve this, and then go and divide this, and then go and get the root of it. It's probably going to be easier. So then what we do is we get this value right here, and we have that value for the bottom, and then we go and we have the 0.42, and this is where we're actually looking for that point and the probability of it being greater than or more than at that point. So we end up with a z-score of 1.29, and then we look it up on the z table, and that is 0.4015. Now, and as I've mentioned in some of my other videos, the last set of videos, I explain a lot of how we set up these questions with the picture and the inequality. And so I'll just briefly mention it. The inequality always points towards our area of interest. Now, when we're doing hypothesis testing, the inequality points towards the rejection zone. When we are not doing hypothesis testing, the inequality points towards our area of interest. It's a subtlety in what we're talking about, but the inequality direction is very important for solving this. And so we go and we draw the picture and it's pointing to the left in this case. The other thing is you want to place your population proportion in the middle, or your mu if you're working with sample sample mean distribution type of setup versus proportion. So you put that one there, and then depending upon whether this p hat is less than or greater than, you put it on the left or right. So if this is, what was this point? So this was 0.40 right here, 0.40, but this one was 0.42. So this is value of 0.42, but because the inequality is pointing to the left, we're actually kind of looking back behind us. And in this case, we put it here, but we actually point the inequality behind us. But it's still greater than 0.40, and that's why it's on the right-hand side. Okay, so draw your pictures. Don't forget about drawing your pictures. So then this whole side, it's complete, and if that's complete, then it's worth 0.5. And this side is not complete. So when we get this value off of the z table, we drop it in right here, and it is right here next to the middle. It's never in the tail, right? And remember, we get the tail values only by usually using subtraction. And that's because in this case, we're adding up our area of interest. If the inequality was pointing to the right, we would still do the same type of math and then subtract all of it from 1. So this is our answer right here. We add this all up, and it is 0.9015. That's our answer. And so the actual math is not much different. Now, in this case, these are proportions, but the actual way that we do this is not that much different than the unit that I made a video for before, working with the populations and sample means. So actually, it was just straight populations. And so that's not too hard. Now, here's something to think about here. When we put this all into the calculator and we use the normal CDF function in the TI-8384 calculator, you need to be super careful here, because when it talks about putting in the when it prompts you for the sigma value, we're not putting in the sigma value that in this case with a proportion, it's not as much of a risk because we weren't given a population standard deviation. But for the sampling distributions, the true sample ones that aren't the proportion, you cannot put in the population standard deviation here. You have to put in the calculated form of that, which is the sampling distribution standard deviation type of thing, or the standard the standard error of x. So you have to put that in here. If you just put in the wrong one, you'll get it all wrong. So, but you can use this the normal CDF function, which is great. Okay, so this is very important if you use the calculator to put in the right value for this, because it's going to prompt you with that. It doesn't know that you're doing sampling distributions. You can still use this function, but it has to be you have to put in the right data for it. Okay, so this is another let's see, this is another proportion one. So we'll look at this. We'll look at this quickly, and then we have a couple other things to look at here. It says, based on history, and I don't know what these, I always make these things up. Based on history, the proportion of those who renew their concealed carry weapons permits is 25%. If a sample of 400 is conducted, what is the probability the number of those who renew to be greater than 22%? So this is a proportion problem. It's a proportion problem because we're given a percentage, but we're not given the population standard deviation. We just know out of the whole population, it's 25%. And then we're given a sample size, and we're looking for the probability that's going to be greater than 22%. So we say, okay, we write down what we know. It's all right here. Okay, we write that down. We plug in the numbers, just like the last one, and we get this one. And this is very important. Remember, don't confuse Don't confuse where, how we work with this. And then we take this right here and we plug it in down here. And then we can get the z-score. Now, since this z-score is negative, all it means is that we're working on the left-hand side of the distribution curve. And of course, we look up on our table the 1.38. There's no negative there. On the table, we still just look for 1.38. And then we get this, when we do that, we get this z-score. And we put that z-score right down there. And then this whole side is 0.5 because it's unblemished. So it's the complete 0.5. And then we just add those up. And once again, we have to put in the correct standard deviation value there. But, and this is something that I mentioned in a prior video, for our upper value on this, now we could do a couple things here. We could make sure that that's a large number, and in this case with the proportions, you have to just make, if you put in the upper of 0.8 or something like that, then you'd be fine as well. But there's one thing that you can do to make sure that your high is up high enough, and that is you take the mean, which is in this case it is the proportion, it's the population proportion value. So you take that. Well, first what you do, you're going to take this and you're going to add it to 4 times the standard deviation. In this case, we don't have the standard deviation, but we have the standard deviation of the proportion sampling distribution, we could say. And so we would take that, multiply it by 4, and then add it to 0.25, and we would get this big number, and that would be our upper end. And all that is to make sure that we don't accidentally cut off some of this possibility in there, because if we cut a little bit off and our high end is not high enough, then we go and we are actually decreasing the total probabilities, depending upon so we're actually cutting off some of our answer, and so we don't want to do that. We'll actually change this answer if we cut off any. Like I said, you could probably, because this is a proportion, you could probably just go and make it really high, which would be like 0.8, and that would be fine as well. Whew, that was a lot to say. But other than that, it's the same type of setup by finding the probabilities of normal distributions. Okay, so this one is the same type of scenario with a proportion, except this one is a between question, and with the between questions, I always go and do this. I write them out. Technically, you can write it out so there's like a 3-segment thing, and it's where you have, I believe you have a value, and then you put the x in the middle, or in this case it would be the p-bar, and then you put your inequalities and then the number. Now, I always recommend just rewriting it so that your inequalities are both pointing towards each other, which makes it so that your areas of interest are in the correct location. So I always do that. I recommend people make it easy. I know it's not mathematically, it's mathematically okay, but it's not mathematically okay that we have 2 statements. That's the part that a purist would say that's not correct, but it works fine. So we do that. Like I said, write down what we know right here. So pull it all apart. And then we have to solve for all of the pieces just like we've been doing. In this case, the differences of the p-hats away from the population proportion are both different. So because this is just a little bit higher than the 50, and this one is a little bit is a greater amount away from the 50 on the low side, we cannot use the same z-score that we calculate because these are different. See, if this was 51 and this was 49, then the z-score would actually be the same. and then we would only have to do one calculation. But in this case, we can't do that. So for these, I usually put high and low when I want to just show what I'm doing the math for. In this case, the negative shows you that it's on the low side. Okay, so these are pretty easy. You calculate out these probabilities, and then you add them up. And as I've mentioned in a different video, I won't ever have the inverse of this where we have the shaded tails, because it's really weird. It's saying that it's like a between question, but it's the inverse of that. I don't make those questions. They're too weird. Then you do this in your calculator and you get the answer too. Now, some of these are starting to be a little bit different than the actual hand calculation, and that's because the calculator number one is usually more accurate. You're not necessarily wrong by having it be off a little bit. If you look at this, this is 0.4098 and this is 0.41, so it's pretty close, but it's actually, in the world that we've been working with, we're starting to get to the point where we have a little bit of difference in that, and that's okay. It's not good if it's far off, like this was 0.49 and this is 0.41. That's a lot, but this is not far off. And I usually don't round. I just write down the numbers, at least like 4 decimal places, so you can see what's going on. And this is so this one I won't focus. Oh, this one's a little bit different. So this one is sample mean, sampling distribution. So we need to take a look at this. Okay, so it says a population with a mean of 1,250 and a standard deviation of 400. Liberal arts degree. Okay, if a random sample of 64 items is selected from the population, what is the probability the sample mean will be less than 1,325? Okay, so you set this up just like we've been setting it up. We write down what we know, and you always do that. Make sure your inequality is pointing in the right direction. And I go over a lot of this. If you need more help with this in the prior unit, where I go over the population, I go over finding the probabilities with a normal distribution in the continuous probability distribution work back there in the videos. So I talk a lot about the way the shading works in the different directions. But in this case, it's the same type of scenario, except we do this. For our standard deviation, we don't have a sample standard deviation, so we have to use this one that we calculate right here. So this is our 400. That's that. And this is our 64. That's our sample size. And of course, if we keep increasing this value right here, then this value, our standard deviation, always have to think about standard deviation of the sampling distribution, becomes more accurate once we start increasing this. So once we have this value, we just plug it right in down here, so that part of it's done. And then this math should be easy, and then we get 1.5. When we look that up on the Z, we take this Z-score and we look it up to get the area under the curve. For the tables that I always teach from are half, they're alternative half tables, so they just only cover one side at a time. So this is 0.4332. And we just bring it right down here. It represents this part. In this case, we're just adding them up, and that's our answer. Now, you can do this, as I've been talking, you can do this in the calculator. And just like I mentioned last time, make sure when it says about the population standard deviation to put in our calculated standard deviation of the sample distribution here, and not the 400, because if you put the 400 in, then you are going to be wrong for sure. So you got to put in the 50 right there. Okay. So do not use the given sigma. So that would be our given sigma is the 400. Our calculated one was the 50. You have to use that. So you have to stop and think about that. Here's the other neat thing, though, is that you can actually, at least in the TI-84 plus CE calculator, you can actually type in this formula. You could type in right here in your input 400 divide by the root of 64, and then as you hit enter and you go down, I think it will actually go and put 50 in there, so it'll actually do the calculation for you. So that's neat. So this is pretty close right here. Okay. So this is the same scenario. So a lot of this hasn't changed from the prior unit, although we're just not using the traditional given sigma value here, or our population standard deviation. We're having to get the standard deviation of the sampling distribution, or standard error of x, and that's all that it is. That's all that these are different. And so I won't spend a lot of time on this because I have one other thing that we need to talk about. That's the finite population correction factor. I know that sounds fun. So remember, I can't stress it enough. You have to put in the calculated one right here. And then this is a between problem, so that's okay. Same scenario. Okay, so now I want to talk about this finite population correction factor. So the formula above for the margin of error assumes okay, according to the sampling theory, this assumption is reasonable when the sampling fraction is small. So what they're saying is the formula that we've been using, which is this right here, is an okay formula to use if the sampling fraction is small. But if the sampling fraction is high, and when we say sampling fraction, what we mean is the sample is large relative to the size of the population. And the only way, and this is a trick thing that I'm telling you, and hopefully other people that aren't in my class see this video, because this will help them as well. Anytime, or unless you have a professor that likes to mess with you, but in my class, anytime that you see for these types of questions a population size, that is a hint that I am doing a finite population correction factor problem. Now, it's possible there could be somebody out there that just tries to, they either give you all of the data up front, and that doesn't necessarily apply for those types of questions, or they're just trying to mess with you a little bit, make it more difficult. But for my questions, if I give you a population size on these questions, it's because you need to be able to see if the sampling fraction is above 5%, or above 5%. So you can't do that unless you know that the population size is of a certain size. And it's a little bit weird because, well, I guess it makes sense. If you can count the population, it's probably not that big. Count it accurately, I guess, would be a good way to say that. So if you can count it accurately, it may not be a super big population. And if that sample is greater than 5%, then you need to use the finite population correction factor. Okay. And that's because when we do that, we're actually changing the outcome by doing the sample. So that's kind of the interesting part of this. It's like that scientific stuff where they say just by interacting with something, you're actually changing it. And in this case, it's kind of the same thing. So by doing the sample, we're actually affecting the population. That makes sense. Okay. So this is the correction factor part. It's this next step over, and it's this big N subtract little n over big N subtract 1, and then you get the root of that. Okay, and then for the sampling distribution one, it's the same finite finite population correction factor um, part that you add on. So both of these are the same. You just add them onto this. Now, I always recommend you do this part and this part, and you kind of do them in pieces and then assemble them, because I always caution students not to try to do everything in one fell swoop, because if you don't do your parentheses right, you're going to get a wrong answer, or you're going to get an error and you're going to have to go back and figure out how to fix it. Okay, so let's take a look at how this works. So usually I give people like at least one of these on a test, just to test you with this. I don't give you a lot of these just because they're a lot of work, but I just want to see if you can do the math. A bank has, let's see, 1,000 different depositors, so we have a population size. So that's a hint right off the bat. Historically, the proportion of this depositors having multiple bank accounts is 40%. If a sample of 200 depositors is performed, what is the probability the proportion of depositors having multiple accounts will be less than 35%? Okay, so this is a big sample. This is 20%. So we have 200, a sample of 200 from 1,000. So this is a big sample. So the finite population correction factor is needed here. And so we write down what we know, and then we just start solving the parts. And like I mentioned before, I would calculate this, calculate that, and then go and multiply them and put them together. It's just easier. And then once we have this, we actually have the denominator for the z-score calculation. So we just plug that right in, and it's real easy. And then we go from there. So we get negative 1.61. That tells us we're on the left-hand side because that's negative. And the z-score is 0.4463. So we put that down here. And this is actually this portion. This is this portion. But because we're looking at the tail, our area of interest is where the inequality is pointing. So it's in the tail. And our math that we can do is it gives us exactly what we don't want. So to get what we do want, we take exactly what we don't want and we subtract it from 1, and then we get what we couldn't calculate really easily, but this is the tail. So 0.0537. And then we do this on the calculator. Yeah, it's close enough. It's definitely close enough. Once again, I caution you to this number right here to put in the right one. Don't jump to the given standard deviation. Just remember, don't throw the given one in, because if you did the given one, well, actually in this one there's not a given one, it's a proportion, but that's okay. On the other ones, when you have a given one, like this one, you could very easily throw 3 in, and you'd be wrong. You would be very close, but you'd be wrong. So this one says, let's see, Jessica Swimming Pups is a pet boarding business that specializes in providing a tropical resort-like atmosphere for one's best friends. Annually, 100 dogs are boarded, who swim an average of 10 minutes a day with a standard deviation of 3 minutes. If 30 pups are randomly sampled, what is the probability the mean swim time will be more than 11 minutes? So they say annually 100 dogs are boarded, and then they say if 30 pups are randomly sampled, so this is a 30% sample, so this is a big sample, and so we have to do the finite population correction factor for this one, and that's what we're going to do. So we do our separate parts, and this is the first part, this is the second part. Of course, it's multiply these two parts, and then we get this answer. And this is the one that will actually go into the if we use the calculator, this is going to be essentially what our standard deviation is for this problem, not the 3. Not the given 3, we use the calculated one, the calculated score. And then we just take this and we plug it in down below, and we get our z-score. And then the z-score, with the z-score, we look at the table and we get the probability under the curve, or the value under the curve, which helps us get our final probability, which is 0.015. And then in the calculator, it's pretty darn close. And I think that's about my last example. I'm trying to think if there's anything that I want to stress. Like I said, I really stress this if you do it in the calculator. So remember that, to always put in your calculated standard deviations, not your givens, if you have one given. And I think that is it. Thank you.